All right, so please do this. Let's get all the desks facing this way. Completely close up the Chromebooks. Because I think it's crucial that you got to kind of be in the moment here for when we're going through this stuff. It's assembly stuff. So the question was asked, how do you get to the notes? Here's how you get to the notes. You go into the Calculus Moodle page, and up at the top where it says Calculus Lecture Notes, you go there. Oh, and what you're saying is you didn't find the notes from yesterday. Yes. Gotcha. Okay, let me pause things for a minute. Let's kind of review very briefly what we looked at yesterday, right? Here's the picture that we have that defines the derivative. Okay, so a couple things from yesterday. We said, the picture we drew here is we said we're going to take the slope of a secant line, right? We're going to identify a secant line at the points x, f of x, and the points x plus delta x, f of x plus delta x. And then we're going to take that slope of the secant line, and by taking the limit as delta x goes to 0, we effectively back this point up to where it overlaps with the first point, and it becomes, in the limit, it becomes the slope of the tangent line, which is the holy grail of differential physics, or calculus, sorry. That's why we developed it. So this part right here, just so you're aware of this, you guys need to know this stuff. This is what we call in math the difference quotient. And it's what defines the slope of a secant line, or an average rate of change. Same thing, right? In the limit, it becomes a tangent line or instantaneous rate of change. An average rate of change, remember, all an average rate of change for a function is just the change over an interval, right? So if we wanted to know on average, let's say we take a function where we have some macroscopic delta x here, and we want to know for some function, what's the average rate of change between, well, I mean, probably we wouldn't be using x and delta x, but if we did, add a page here and make a point. So if we've got some function, like let's say we're looking at, we'll make a physics problem here. Say we're looking at position versus time, right? And our function's doing something like this, something like that. Okay, we want to go from this point right here at A to this point up here at, whoops, how about right there, at B. You pick what A and B are, it doesn't matter. If we want to find the change in position over change in time, the slope of this thing, right? The slope of this line between these 2 points. So that's going to be x of B minus x of A over B minus A. Well, what's that look like in physics? We're looking at a delta x, right? The slope of that line between those points is just delta x over delta t. What's that look like? No. Change in position over change in time? Velocity. Well, average velocity, right? So it's an average rate of change, isn't it? You can see that the instantaneous velocity is changing all over the place in between there. But we don't care. All we're talking about from point A to point B, or for time, maybe we make this from 0 up to t, might be better. That's what we would do in physics. Right? And so then we'd end up with delta x over t minus 0, delta x over t. And that's just our definition of average velocity, isn't it? Right? Displacement over time is average velocity. So over that interval, we can define an average rate of change. We use the example of going to Hermiston in a car, right? If we're going to Hermiston in a car, we go 30 miles in 30 minutes, our average velocity is 60 miles an hour, but we may have rarely actually ever gone 60 miles an hour, but that's the average, okay? So we associate then, my whole point there is, we associate an average rate of change with the slope of a secant line. That's what it is. Secant line, remember, connects 2 points on a curve, and the slope between those points is the definition of an average rate of change. Instantaneous rate of change is what we just did, right? We just found the slope of a curve, right? So in physics, that would correspond to an instantaneous velocity, right? You get that? We answered questions like yesterday, like this one, right? We wanted to find, didn't we calculate a tangent line here? Yeah, we calculated a tangent line for the curve y equals x squared at x equals 2, right? And so we found out that the equation of that line was this, right? Now, we wouldn't have to go that far in physics, but if we wanted to find out what the slope of the function was at 2, well, that was just 4, right? We just calculate the derivative, and we evaluate the derivative at 2, and it gives us back an answer of 4. If this function were position versus time, that would be telling us that the instantaneous velocity at t equals 2 was 4, right? So you can see how in physics and calculus just go together, right? So we talked about in physics about how we don't really have the ability, those who are in physics, we don't really have the ability to have the math toolkit in a physics class to find an instantaneous rate of change, but now we do, right, in calculus. That's how we do it. It's just the derivative of a position function, okay? And you'll do some problems like that. Okay, so we ended up, we didn't finish this one, right? Okay. Why don't we go through one of these? Let's finish this one up, because it's good to see. I want you to see how this works. Here's kind of what I want to do today. I want to just reinforce what we learned yesterday, but then I want you guys to come up with an alternate form of the difference quotient that we could use for a couple of reasons. I want you to see that you can use your imagination and just follow the rules, and we're going to find another analogous form that works just as well. In some cases, maybe better. And then we're going to use the form you come up with to talk about how continuity relates to the existence of a derivative. Okay? We won't get through all that today. That's kind of where we're going with this for the next day and a half or 2 days. All right, so let's go through this example first here. Our function is this, right? We want to calculate what the derivative is first of all, and then we're going to find the slope of the curve at 3 and find the equation of the tangent line, right? But the calculus part of it is just taking the derivative, right? The rest of it is just algebra. Okay, so then we're going to use our definition of a derivative. The limit of the difference quotient is delta x goes to 0. And that's where we left off, right? So we want to start general and get specific, right? So this is the general form, but being as we are given a specific function, now we've got to take the general form and write it in terms of our function, right? You told me yesterday that f of hand was hand cubed plus 2 hand, right? So if hand is x plus delta x, then there's the pattern. I get x plus delta x cubed plus 2x plus delta x, right? That is f of x plus delta x in green. Minus f of x is just a quantity x cubed plus 2x, right? All divided by delta x as delta x goes to 0. So at this point, I've got 0 over 0. Everybody see that? If I try to evaluate my derivative, the delta x's drop out, so everything on top would cancel. The bottom would go to 0. This is just the limit stuff that you've had quite a bit of practice with. So you kind of get a sense of how this is going to work. We're going to have to simplify the top to the point where we could factor it and cancel the common factors that are causing it to be indeterminate. Well, what do you think those factors are going to have to be? Don't just leave it to chance. As much as you can, if you want to be a good mathematician, you want to kind of hone your strategy to the point where you have a pretty good idea what needs to cancel even. Okay, so those are going to cancel horizontally. You're right. What's going to have to cancel vertically here? The delta x's, aren't they, right? Because that's what's going to 0 on the bottom. So I'm going to have to, at some point, I'm going to have a common factor on the top of delta x that I can cancel with the delta x on the bottom. You see that that's what has to happen. And it will. It will happen because we can take a derivative of this function, right? I mean, this is, and you'll have a better sense of why you can in a day or two, right? You'll see in about a day or two that this is a continuous function, and so the derivative is defined. That doesn't make sense to you right now, but it will, like next Tuesday. Right? You'll be able to look at this and say, okay, I know I can take this derivative, so this has to work out. So if I'm not getting this stuff to happen, I'm screwing up somewhere. I better go back and look for my mistake. Okay? Okay, but for now, let's just plow through this. So if I expand that out, what do I get?
X cubed plus 2x delta x
Plus,
2x squared delta x.
not 2.
These
Should be, if we're cubing out a binomial,
delta cubed.
3. Good, it's a 3. 3x squared delta x plus
3 delta x.
3x delta x squared, good, plus, you guys remember this expansion? Okay, this is, you know what, I think, I'm not a huge, I don't often make people memorize a lot of stuff, but in calculus, sometimes there's some things I am going to want you to memorize. Here's a couple things you need to memorize. Take a little break. So, just for a second. These are binomial expansions you use constantly. So you got to know these. Obviously, you guys know this one, right? A plus b squared. Let's do a plus or minus b squared equals what?
B squared.
Plus or minus. Plus goes with plus, minus goes with minus. No. 2ab. No, just plus. B squared, right? See how that works? If that's a plus, we use the top signs. If that's a minus, that first one becomes a minus, right? Okay, how about this one? A plus or minus b cubed. A cubed plus minus 3a squared b plus, is that right? Plus, yeah, that's right. Plus 3ab squared minus, plus or minus b cubed, right? So those are two you really want to know. Those are, and then beyond that, you guys, did I review Pascal's triangle with you?
No.
Okay, let's do that. I mean, because you're going to be doing lots of expansions here. You're going to be doing you're going to be doing some fourth degree binomial expansions and things too. And so the binomial expansion formula, I never remember it. I have to always derive it for myself every time I use it. It's, that's just, I don't want to waste those brain cells memorizing a bunch of stuff. But Pascal's triangle is a process that anybody can do. So here's Pascal's triangle. Let's review this real quick. So for Pascal's triangle, you know that what you do is you start with a 1 at the top. You can build it, right? And then you're just going to have 1s down the slopes of the mountain, and in between, you're going to get the sum of the numbers above, right? So 1 plus 1 is 2, right? Here I get 1 and 2 makes 3, 2 and 1 makes 3. See what I'm doing? 1. What's this next line going to be? 4. No. 6, right? Because those guys go to 6. 1. Next line. 1, 5. Okay, and what this corresponds to, right? These are just the coefficients that we would get if we expand out a plus b to the n, right? That's terrible. You can't read that. Jeez. Okay, so, and then this first row corresponds to, this is the n equals 0 row, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, etc., right? We just work our way down. Okay, so these are just the coefficients. So what this first one up here is telling me is that if I wanted to write out, for example, a plus b to the 0, the answer is just, yeah, it's just 1, right? Anything to the 0 is just 1. What's this telling me right here? This is telling me that a plus b to the 1 equals 1a b to, so this is really, I could go a little further than that. I could say this first one is 1a to the 0, b to the 0, okay, which is equal to 1. The second one is 1a to the 1, b to the 0, plus 1a to the 0, b to the 1, which is just a plus b, right? How about this one? I better choose a different color. So this one means 1a squared b to the 0 plus 2a to the 1 b to the 1 plus 1 a to the 0 b to the 2, which is just a squared plus 2ab plus b squared. And honestly, we don't really need to put the plus or minus there, because if b is a negative number, it would take care of itself anyway, right? I usually don't even write them with a minus. I just write them with a plus, and I know if b is negative, then every time I get an even power of b, it's going to be positive anyway, and the odd powers are going to be negative, right? So, okay, do you see the pattern? See what we're doing? So you tell me, what's the next one going to be then? 1. How do the exponents, what's the game we're playing here? You can see the coefficients, obviously. These are just the coefficients. But how do the powers of a and b relate to n? What's the sum of all those exponents in this row? 2, because n equals 2, right? The weight of the exponents always starts shifted towards the first variable and incrementally just steps down from the first and up to the second, right? So a goes from 2 to 1 to 0, while b goes from 0 to 1 to 2. But the sum is always n, which is 2, right? See how that works? Simple, okay? So we could jump down to something like the last one here, and that tells us that a plus b to the 5th equals 1 a to the 5th, b to the 0, which we wouldn't write, that's just 1, plus 5 a to the b plus 10 a to the 3rd, whoops, oh gosh. B squared plus 10 a squared b to the 3rd plus 5 a b to the 4th plus b to the 5th. You can always just, by just cranking out that triangle real quick, you can expand any reasonably sized binomial pretty quickly, right? Like you can go down pretty comfortably down to n equals 6 or 7. Beyond that, probably you want to just use the binomial theorem, right? But does that make sense? Okay. Tell me something else here, because there's always another level you can look at this. What do you notice about this pattern in Pascal's triangle? Do you notice any symmetry?
The second row in is 2, 3, 4, 5.
That's true. Yeah. Yeah, look, you notice there it's 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Do you notice the symmetry to this? Do you see that it's got an even symmetry about the midline? the coefficients have to be equally distributed, right? It has to have reflective symmetry in a sense, right? Explain that. Why is that true? It has to be, if you think about it. But I want you to see this insight, because this is something you can use this way of thinking in the future. How come that has to be that way? Those are coefficients, right? Agreed?
It's like they are built in the function that's being raised to another power, so they have to be the same.
Right, so these are the coefficients for the expansion of a plus b to the n, right? How is that related to b plus a to the n? Same, right? Because we know that addition is commutative and associative, right? I can interchange those two. You agree? So this formula has to account for that, right? The math gods are smart. They know that because I can interchange A and B, there's no way that this could be asymmetrical, because that wouldn't allow for commutivity or reassociation of the terms, right? The math gods know what they're doing, right? So it has to be that way. You have to have this kind of symmetry, don't you? Right? Okay, questions on that? All right. So let's go back then to our problem. So then we end up getting, if we expand this, that's what we get from this part, right? That comes from there. Plus 2x plus 2 delta x minus this stuff. And let's go ahead and distribute the minus sign. How about it? All over delta x. Okay, well, what has to happen here? I mean, what does happen and what has to happen? Okay, so before we factor out what can we do? Horizontal cancellation. We have to be able to, right? We can see into the future here. We can see that we have to be able to cancel the common factor delta x. Well, to be able to factor out the delta x, all the terms in the top have to have a delta x in them. So all the naked terms that don't have delta x's have to get canceled. And they do. X cubed minus x cubed. 2x minus 2x, right? And so what do we end up with then? Just what we need, right? We get the limit of 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x all divided by delta x. So now I can factor out a delta x, right? And what's left behind if I do that?
3x squared plus 3x delta x plus delta x squared plus 2 over 1.
Right? Okay, here's my vertical cancellation, right? So I'm left with just this expression, and now I can evaluate my limit. As delta x goes to 0, every term that includes a factor of delta x in it goes to 0, and so I'm just left with 3x squared plus 2, right? So that's my derivative function. Okay, so now I know that I started with f of x equals x cubed plus 2x. Now I can add to that the derivative function, f of x equals 3x squared plus 2, right? Okay, so before we go any further, let's just graph both of those on the same graph and observe the behavior when we do that. So, okay, so we got Okay, good. Let's call this one g of x. That'll be the derivative. Okay? So original function's red, derivative is blue, right? Let's explore this a little bit. What if I take, what if I take, for example, let's evaluate the derivative at 2. Okay, so I'm going to need to maybe, how about if we, here, I'll show you something else you can do with this then. So in order, if we want to use 2, these functions are off the screen at 2. I guess I can just do that, for now. What if I want to compress the vertical axis, but keep the horizontal axis the same? Do you know how to do that? It's handy to do. You go into here, click on the wrench, and then you can go down here and control independently, like the x-axis and the y-axis. That's really a good feature, okay? So let's calculate f of 2 and g of 2. Actually, we didn't really need f of 2, but I did it anyway. So what's the significance of f of 2? Well, that's just telling us a point on the curve, right? Okay. What's the significance of g of 2? What's that? G is the derivative function. It's g. I had to write a g. I can't write an f prime on here for reasons you'll see in a second. But if g is the derivative of f of x, what's the significance of the value of g of 2? What's the derivative tell us? Okay, slope of the tangent line, meaning the slope of the curve. Same thing, right? You can think of those as being one and the same. The slope of the curve at 2 is 14, right? So what does that mean about our, if we were to write a tangent line to the curve at that point? It's got to have a slope of 14, right? Okay, so if we wanted to very quickly, let's just show this. If we wanted to take this information right here, and we're looking at, well, let's use 2, how about, being as that's what we're using in our example on the graph. Well, okay, so there's our function and our derivative, and we want to find the slope of the tangent line, how about, at x equals 2. Well, the slope of the tangent then is just f prime of 2, which is, we said is 14, right? 3 times 4 is 12 plus 2 is 14. And a point on our curve is at 2 f of 2, right? What's f of 2? 12? Is that right? So then we get y equals 14x plus b. To solve for b, we'll just plug in a solution, right?
Did you get that? Everything was complete?
Because the slope of the tangent line is 14, right?
Yep.
So that's just going in there.
Yep.
And so then we get 12 equals 14 times 2 plus b. So what's that going to give us for b? 12 minus 28 is what, negative 16? So there's B, here's M, right here. So those combine to give us the equation y equals 14x minus 16. Let's graph it. X minus 16, what do you know? Okay, if we turn off our derivative function, let's just turn on these two. Well, where's the point of intersection? How come it's not sticking? Oh, there it is, right there. I had the wrong point. There it is. So there's the point of intersection, 212, right? That makes sense, doesn't it? That's consistent with what we saw, right? There's our point of intersection at 212, right? Oops. And notice that the slope of this line is 14, right? Okay, so beyond that, let me go ahead and expand out the x-axis a little bit. So let's let x go from, how about, well, actually I'll zoom in a little bit. So we're going to go from like -10 to +10. Okay. Did the shapes of these curves make sense? Actually, these curves make sense. The blue curve is the derivative function, and the red curve is f of x. So blue is f prime, red is f. So explain to me why, for example, why there's a minimum of the blue derivative function at x equals 0. It's not 0 there, is it? What's the value of the derivative function, though? Something like, it looks like it's about 2. That's its minimum value. How does that work? How does that correspond to the behavior of the red function? See what I'm saying? Okay, what is the, and this is what you got to kind of wrap your brain around here. And it takes a little practice. What is the value of the blue function equal to? The slope of the red function, right? Yeah, so the slope of the red function is the value of the blue function. Well, qualitatively, what can you tell me about the slope of the red function here? It's large and, no, the slope. Large and positive, isn't it? Right, if I drew a tangent, would everybody agree at this point right here it's large and positive? So if I look straight up, what do you know? The value of the blue function is large and positive. As the ant walks along the red function, it's getting less and less steep. It's positive, but it's getting less positive. Smaller in magnitude, right? Well, what's happening on the blue function? The value is positive but decreasing. Would everybody agree that at this point right here, which we'll come to call a point of inflection later in the class, this is the minimum value of the slope, right? This is the place where the mountain that the ant is climbing levels off the most, right? Yes, sir.
Why not? It's touching. Why is it like touching? If it's like asymmetrical on this high positive,
Say that again, Rylan.
So like, why doesn't the minimum of the blue slope touch right where the red slope is coming up above 0?
Because it doesn't have, there's no reason that it would necessarily. See, this is an example where it would have if the red function had become horizontal, but it doesn't. It's all that we know here is that if I look at this red function, it's got some symmetry about that point. That's going to be the point where it's at a minimum. Everything to the left of that, the ant experiences a positive but decreasing slope. Everything to the right, the ant experiences a symmetrical, positive, increasing slope, right? Well, notice that this blue function has symmetry about the y-axis, right? It has that even symmetry. But the vertex of this parabola doesn't need to overlap with this thing, right? But do you see the behavior there? As the ant continues along to the right, his slope is increasing, and so the value of the blue function is increasing, right? This ought to look pretty similar to what we talked about in physics.
Top left. on the Chromebooks are dead.
Okay,
The other half, I don't know.
okay, gotcha, thanks.
Sorry I was so late, I had a college meeting.
Oh, you're fine, yeah.
Hey, do
no
we have
sweat.
to go to our, PI class? We can just right there. Right there? Alright.
Yeah.